that should work right.
I don't know what you're talking about, Space Ghost.
Go ahead,
My
Mulgar.
show was...
Yeah, we poked you with sticks till you fell down. Remember?
You sure I didn't harness the power of the sun?
No, it's definitely sticks. Beaten with sticks.
All right, go get 'em. How's it going, man? Ow!
Oh, you knocked him out. Give me that stick.
Ow! Not there! Ow! Ow!
Are you still here?
Welcome to the program.
I'm sorry. I thought the show was over.
It started?
Yeah, oh yeah.
Okay.
my great honour to welcome you all.
It is a very prestigious award. It means the world to me.
They have great senses of humour.
I like to reveal parts of history to them, for I love making history come alive.
They are some of the best people that you can come across.
To help them open their hearts.
I always come back to this quote. How can we be role models to learners if we're not learners ourselves?
It's quite useful to get out of our bubbles, not our COVID ones, and sort of see what else is out there.
By sharing best practice, we can see the whole picture. We can see what really matters.
One of the biggest brains around.
It's easy to forget how much has to happen behind the front line.
As a global schools group, Cognita educates over 55,000 students across 12 countries. We're proud to be Wellbeing Partner at this year's Festival of Education, and we want to share the work that we're doing to prioritise children's well-being. This starts with a clear understanding of what well-being is. We looked at the evidence and created a simple Be Well Charter that everyone can use day to day. It gives a clear definition of well-being and then focuses on the specific contributors that influence it. Discover our full Be Well Charter video and other resources to use with your students and families at cognita.com.
I really try to not look at myself as just a science teacher. I feel like as a teacher, it's very important to help students grow and develop outside of your lessons. A single teacher believing in you and really believing in you. One teacher doing that can have a large impact, but if you have one or two or three all telling you that and really, really believing in it, it makes you feel like you can achieve anything in the world, honestly.
Welcome to this Festival of Education keynote session, part of the annual Festival of Education, taking place online from the 16th to the 30th of June. This year's festival is free for all teachers and educationalists across education in the UK and beyond. This has only been possible thanks to the support of our incredible partners. A huge thank you to our headline partner, Pearson, our festival partners, BBC Bitesize, Cognita and Teach First, our literary festival partner, Bloomsbury Publishing, and our organising partner, Wellington College, the home of the Festival of Education. We'd also like to thank our incredible speakers. Over 200 leading educationalists and thought leaders will be providing sessions at this year's festival. On behalf of the audience and organisers, thank you. It's time to sit back and get set for our upcoming keynote session. If you wish to ask a question during this session, please head over to our Slido page to submit questions and vote for your favourites. Enjoy this Festival of Education keynote session.
Hello, my name's Jess Easton and I'm the Head of Training and Development for White Rose Maths. Influenced, inspired and informed by the work of leading maths researchers and practitioners across the world, White Rose Maths brings together a team of highly experienced and passionate maths teaching experts to train, guide, help and support all the mathematical teachers we've got in education at the moment. In this short video, I wanted to talk to you about post-pandemic learning and how White Rose Maths can help you in the classroom and beyond. I don't think anyone would have been able to predict these last 2 academic years. From the first lockdown to the current blended learning approach with bubble closures left, right and centre, we know it's been a real strain on you as teachers. But what does the future hold? Well, we don't know that, but what we can do is the best we can to support you through this journey. First, let's consider the barriers we're facing come September. Do we know where pupils are and what they're about to teach and where they're starting from? Will we still have to manage some of that kind of blended learning approach? Is there too much to get through? And do we know the gaps in learning for each individual child? All these barriers are big challenges to deal with. So how can White Rose Maths help? Well, let's look at some maths. This is a great question from our premium resources, looking at multiplication of fractions. This question is one of my favourites, and it not only allows some fluency practice, but it also relies the learner's reasoning and problem-solving skills. Some students may answer the question just one way. They may not have the systematic approach to the question, but a trial and error approach will work just fine to get some solutions. Familiarising themselves with the structure of the multiplying fractions. To extend their thinking, we could ask, are there any other ways to complete the multiplication? Or, which has the most options and why? With students who are struggling with the task, you could provide support in the form of arrays, asking them to see what multiplications these diagrams represent and how these diagrams represent the multiplications. Once the learners have had time to grapple with the problem, you can then discuss more systematic approaches so that they know that they have all the options. More discussions can happen here, looking at examples like 1 over 1. Is this a fraction? Or 18 over 5. Is this a fraction? These discussions not only allow you as a teacher to assess what the students are thinking about, but also will help them understand the concept even further, making links between many areas of maths. Asking a question about what do you notice may draw out the idea that actually 18 has the most factors. We can also see that 1 has the fewest factors. In fact, it only has 1 factor pair. Another interesting one to consider is 5. 5 has 2 factor pairs. Is that the only option? Is there another number that would have 2 factor pairs? This could evolve into discussions that support even further, and you could ask that question to kind of test their understanding. Can you think of an example where we give even fewer options than the options that we have now? We could consider things like prime numbers and square numbers, and then support the students to answer the question like this. The point of showing you this example is to show you that one question can be used for all children. With the right scaffolds and extensions in place, this could give students all students in your classroom the opportunity to practice multiplying fractions in many different ways, really understanding the structure behind the maths, but also being able to extend, spot patterns, and make connections from other areas of the maths curriculum. So how can White Rose Maths support you? Well, as I said before, this question was one from our premium resources, which for a small cost to your school will give you access to hundreds of small steps where each have home learning videos. They have the teaching slides to those home learning videos. They have true or false questions. And they have the worksheets themselves, which come in a variety of different forms. For secondary practitioners, we also have your schemes of learning, which are completely free. We have a flashback forwards, which are nice little starters to get you going at the beginning of each lesson. We have those exemplar questions for each block, which gives you an array of questions that you can ask in the classroom, which are editable. And you have your end of block assessments and end of term assessments. We've also put in some lower attainment guidance for you. For primary practitioners, we have, again, the same free scheme of learning, free flashback fours, but this time we have an editable reasoning and problem-solving questions. And then, of course, you've got your end of block and end of term assessments as well, which are all free. As well as our resources, we also have, and from September, are bringing back face-to-face training, which we're really excited to come back to visit you in your schools. But if face-to-face is not up for you right now, we also have a lot of webinars that you can choose from, and you can come as an individual or as a group, absolutely fine. Finally, I just wanted to leave you with some top tips from us when you are thinking about planning for September. First, take your time. It's going to be a long process. There's not a magic wand, but if you focus on the key ideas in maths, the rest will come. Secondly, choose questions and activities that will work for all children in your classroom, considering how to support and how to extend. Listen to the dialogue in your classroom. You'll be able to assess where the learners are and extend them further. And don't panic. We're all here at White Rose Maths to support you, and everyone is in the same position.
So hopefully you've enjoyed this little maths warm-up with White Rose Maths. But up next for the main event, we have the wonderful Johnny Ball, who I'm really, really looking forward to stepping back in history with on his talk on the wonders beyond numbers. Johnny, over to you.
Hello, and hello everybody. Hope you can all see me. I hope you can see the framing is all right, because they won't have told you this, but I actually thought this was Friday, and it was only 20 minutes ago. They reminded me it was today. I think as I get older, my brain gets more flippant. But anyway, I've got a talk for you today, and it's all based on my book, Wonders Beyond Numbers. And Ian Stewart, who reviewed it in the first place, reviewed it again because he read it again about a month ago. And he came back. I don't know whether you know Ian Stewart. He's probably the most prolific maths writer that we have in this country. And he read it again. And he said, it's quite brilliant. Had I found this when I was a teenager, I would have devoured it. And that's why I'm showing it now, because it's for a secondary school pupil from 9 upwards. And it's meant to be readable, and it's meant to be read and understood and not to confuse in any way. So, and the story is based on that. Okay, the talk. So here we go, and off we go. I have a lectern here. See, I could use PowerPoint, but that means me flicking around with things, and it gets very confusing. So I use a lectern, and this is my lectern. Those are my other 2 books that are out at the moment. They've just been re-released as all about numbers and all about maths, but they've been around and sold many, many thousands. And this one, as Go Figure in America, is in the Chicago Depository of Great Books. Wow! So there we are. But that's the commercial over. What I'm going to talk about now is the history of maths. And one of the first, arguably the first great mathematician, was a man called Thales. And Thales lived 2,500 years ago. And he definitely studied maths with the Babylonians, and he definitely went to Egypt. In fact, in Egypt, he explained how you can measure the height of a pyramid. And it's so simple. Basically, what he said is you use similar triangles. So what I have here, can you see that? Is the pyramid. He didn't cut a quarter of it away. It would have taken too long. So he didn't get a pick and cover. But that's what you do. All you do is you get a stick. Ideally, if the stick is 1 meter tall, above the ground, so you need a bit more to stick it in the ground. Okay. And then you wait for a nice sunny day. And as they shine down, the sun's rays will cast, I'll be bound, shadows too on the ground. That's the stick and the building or tree that you want to measure, in this case, a pyramid. So you measure the length of them both. Yes, there's 2 shadows, length of them both. Divide the stick shadow's length into the length of the shadow of the building or tree, and it will tell thee the height of the thing, be it tree or building, in meters, quite precisely. And it's so simple. So you've got to do this, and you've got to get your kids to do this. Okay, and because it's a lovely exercise. Now, the point of all my talk is that I believe we neglect geometry at our peril. And that's why we don't produce as many scientists, engineers, technologists, draftsmen, not draftsmen, they went years ago, architects, people like that. You can tell this is ad-lib, can't you? Right. Architects, we don't inspire enough of them because we concentrate too much on numeracy. And numeracy is fine, except machines can do numeracy. We don't need to do numeracy. And I'll explain how the Greeks did numeracy, or rather didn't do numeracy, in a moment. But that was Thales, and he started. But he did lots of other things. And he led, next thing led to a chap who followed him, who most people have missed, and his name was Hippocrates, not Hippocrates the medic. That's Hippocrates from Kos. This is Hippocrates from Chios, who lived at the same time, okay? And Hippocrates from Chios was quite incredible, and he produced a couple of ideas. He showed the Mesolate compass, and really, I've already done the thing here, but I'll explain what it is. To multiply any 2 numbers, all you need is 2 straight lines at an angle. And you might say, what is the angle? It doesn't matter a jot. But for this, you can multiply any 2 numbers, divide any 2 numbers, or compare by ratio any 2 numbers using this Mesolate compass. It's so incredible. I have to explain that the Greeks didn't do numeracy. They didn't even give their numbers names. 1, they called it A, alpha. 2, they called it beta. 3, they called it gamma. 4, they called it delta. They just used the alphabet. So they really didn't do numeracy, but they knew how they could do numeracy. My mail's come, just come in the letterbox. Right. So what you do, say you want to multiply 42,642 by 9, no, hang on. 3 times 4. Say you want to multiply 3 times 4, right? What you do is you find 1 on the bottom line. Every journey starts with 1 step. So if every mathematical problem starts with 1 step, you could develop from there. So you've got a 1. You want 3 4. So you find 3 on the top line and you put a line through the 1 and the 3. Simple as that. You've got a picture of 1 3. Now think about this. 2,500 years ago, maths in pictures. 2,500 years ago. Isn't it incredible? So you've got a picture of 1 3. You want a picture of, you want 4 3s. So you draw a parallel line through the 4 on the bottom line, and it'll go through the 12 on the top line. It's as simple as this. It's so powerful. Not only that, you can do all kinds of things with this. So what I'm going to do is I'm going to go along here, and I want you all to shout stop. Now you'll all shout stop at a different time, and I can't hear you. So I'll stop when I want to. Stop. There, right? Say I wanted to measure or divide this line from here to 0, right? I don't even know. I stopped in between 2 blobs. I don't know how long that distance is. And because we're on projectors, we couldn't possibly tell because it's different for everybody. Okay. But if even not knowing that distance, could I divide that distance exactly to the millimeter into 3 pieces, 4 pieces, 5 pieces? Yes, I could, using this. And how? Well, it's so simple. All you need to do is find your point, right? And say you want to divide it into 5 pieces. From the 5 point, you draw a line through it, okay? And now you want 5 pieces, so you draw a parallel side of the 4, 3, 2, 1, and you divided that line exactly into 5 pieces without even knowing its length. And if you do it accurately, it can be accurate to the millimeter. Isn't it incredible? So that's one thing. But the next thing he showed, you got to remember, Hippocrates should be more remembered, but we've lost virtually everything. But he wrote a book called The Elements. Now, there's a book called The Elements written 150 years later by a man called Euclid. But Euclid could even have been a scribe. He may not have been a mathematician. We think he was. And he was the head of the Library at Alexandria. And they would have had a copy of the Elements by Hippocrates, and it's lost. But I might be talking about the greatest mathematician that ever lived now, but we don't know. I think he's wonderful. Right. He showed how to find the square root of any number, and they didn't do numeracy. What? Let me show you how to do it. I sort of got ahead. Say you want the square root of 32,000. No, hang on. Say you want the square root of 9. Fine. There. All you do is find 9 on the bottom line, okay? Then you add 1. Now, why do you add 1? Because that's what makes it work. So you got 10. You find the center point, 5. With the compasses, you draw a semicircle joining the 0 to the 10, okay? You raise a perpendicular from the 9, and in every case, the length of that line to the circle, to the semicircle, is exactly the square root of that for any number. So if you chose 10,000, added 1, found the middle point, drew the semicircle, then the upright will be 100, because 100 times 100 is 10,000. It works for any number. It's unbelievable. So where did this come from? Well, I'll try and explain. Yeah. First of all, because we chose 9, it's not too clear. Can you see that? First, we got 9 here, and because we chose 9, 5 is the center point, so that's the radius. What we got left is 4, and that is 3, and it's your 3, 4, 5 triangle. But that wasn't the inspiration for this. The inspiration was this. Still hope you can see. Can you see it? Is it pale, but you can see it? Fine. Right. What you do, if you take any point along here, as Thales told us, and form a triangle, that angle will always be a right angle. It's half of a circle, and it's a right angle. When you think about this, how could he have discovered this? He might have had a table, a rectangular or a square table, and drawn a circle around it, and found that, oh, look, the diagonal from corner to corner across the table would always give me a right angle. So that's what we have. We've always got a right angle. If we drop the perpendicular here, you've got 2 triangles. They are different, but they're similar. The angles are all the same. That angle equals that angle. That angle equals that angle. And those 2 angles are equal because it's half 180 degrees, 290. So, excuse me. So, I've got no glass of water or anything. So if I'm going to start coughing, I'll be coughing for the next hour. So, right. So this triangle and this triangle are similar. And so their sides are always in proportion. So I've given that the value of 6. If that had a value of 3 and that is 6, this would have to be 12 units. It would have to be. Because 3 to 6 is a 6 is to 12. This is how they did their maths, using ratios and proportion. I've heard that over the last year or so, there's a lobby to take ratio and proportion out of teaching children mathematics. I've heard that, and I think it would be disastrous. Right. If this was 2 and that was 6, that would have to be 18. 2 to 6 is 3 more. 3 but times 3. So 3 6 is 18. But if that was 1 and that was 6, that would have to be 6 times 6 or 36. So whenever you do this, you get the square root. Now, I'll tell you another fascinating thing here that isn't normally in my lecture, but I'm going to tell you, and you must write this down and work about it and think about it. Draw a circle, right? Draw any circle, any size, put a dot anywhere in the circle, okay? And then draw a line through the dot across the circle. And then draw a line through the dot another direction across the circle. So if this first line is AOB going through O the dot, okay? And the second line is COD, right? You happy? Multiply AO times OB, and then multiply, you need a calculator, don't worry, do it now, don't do it now. And then multiply CO times OD, and what do you find? This will blow your mind. The answer is always exactly the same. Now that's in Euclid, and we don't teach Euclid. But Euclid inspired Lady Ada Augusta Byron, for instance, the first computer programmer. Einstein, very much. Who was the great president who was shot? Abraham Lincoln. Abraham Lincoln always carried Euclid in his saddlebag, right? Einstein called it his little magic book. Right. And if you study Euclid and take bits out of Euclid and give them to your pupils, you can inspire them about the possibilities in mathematics. And we're ignoring that today. These are just a couple of examples. Now, these examples were spotted by a man called René Descartes. And Descartes wrote a book called The Geometry, in which he explained these two problems that I've shown you. How to multiply using two lines, and how to find the square root of any number. That was his intro to the geometry. And he then said, so do you see, with a few known lines and known angles, you can calculate absolutely anything. And he was wrong. Because then they couldn't measure things that changed or fluctuated. They didn't have calculus, but that was the kicker for calculus. It was then that it started, the search. He, Descartes, and Fermat began to look for calculus. And once we got calculus, the ability to measure things that change as they change, then we could measure anything. That was the beginning of the Industrial Revolution, not the steam engine. Because you could do the maths, and only if you could do the maths could you understand which steam engine was better and why. It's the maths that's at the core. Okay. Is this too heavy or too light? Are you enjoying it? Shall I carry on? Right, let's go on with something else. Right. There's a lad called Eratosthenes. Eratosthenes also mentioned these the things that I've just mentioned, but he lived a lot longer, a lot later, right? He was also the boss of the library at Alexandria, and he heard a story. He heard a story that in a place called Syene, which was south of Alexandria where he lived, the sun shone straight down the wells, but only on one day a year and only around noon. Wow. The sun shone straight down the well. So he said, so the sun must be directly overhead. But it's never directly overhead in Alexandria where I live. I wonder if I can use that to advantage. So he found an obelisk. Now, this was 2,000 years ago, right? The obelisk was almost certainly 2,000 years old then. So he's using a 2,000-year-old tool, if you like, to produce a mathematical trick, right? So he measured the angle of the shadow of the sun at midday precisely on Midsummer's Day. And he found the angle was 7.2 degrees. That was incredibly lucky. Or he massaged the figures. It's, you know, because if you divide 7.2 into 360, it goes exactly 50. So he said, that means if I measure the distance from Alexandria to Syene, which was almost directly south, right? Then I should have 1/50th of the distance around the Earth. And from that, I can measure the size of the Earth. So he did it. How did they measure it? They paced it in those days. They had an understanding of camel days, how long it took for camels to travel. But of course, that would vary between good conditions and bad conditions. Stormy conditions, it took longer. And so that was accurate. So they paced, and they actually paced everything. They really did. The Romans paced everywhere, and they always knew, the Romans, whenever they pitched camp, they stuck a stake in the ground, and they always put a sign up, to Rome, so many miles. They always knew, right? So I tried to illustrate this when I did a television program. So I put a tape measure down on my carpet in the living room, right? And I walked around till I'd warmed up, till I was really marching. And then I walked along the tape, and my wife spotted where my toe started and where my second toe, a double pace, so I could know finished. And we found it was 1.75 yards. Now I've used that, that's figures precisely, 1 3/4 yards, 1.75 yards. Why did I do that? Because 1,000 of them would be 1,750 yards, and a mile is 1,760 yards. So the first time I tried to pace, I was only 10 yards out in a mile. So no question, there's a phone call. I can't speak now, I'm doing a lecture. Bye. That was my wife saying she's coming home, right? So the Romans could pace so accurately, and everybody, so they paced it out, and it's about 800 kilometers from Alexandria to Syene. Times 50, you've got a distance around the Earth, 40,000 kilometers, which when we went metric, that's the figure they gave it, and that was it. The sad thing was, nobody believed Eratosthenes. Why? Well, here we go, juggling about. Stay there, I'm not going far. I have the Earth here, right? And this, where am I? There we are. This is the map Eratosthenes produced on the Earth, okay? It just went to the west edge of Africa and around here past India, and it had Great Britain in it, okay? But they knew nothing below the equator very much at all. That is, at the most, 1/10 of the world. So when the Greeks were told that was the size of the Earth and they only knew that much, they just didn't believe it. They didn't believe there's so much they didn't know. So a chap called Poseidonus, he was a stargazer and an astronomer, very good, but his maths wasn't that good, right? And he measured, and he came up with a map, okay? And a couple of hundred years later after that, the map was redrawn by a man called Ptolemy. And this map is in lots of books, and it's come down, and there it is. Great Britain is straggly up here. The Mediterranean is much too big. Okay, it's much too big. India, look at India. They've no idea of its shape. Look at the bottom of Africa. They've no idea. So they really didn't know a great deal except around this area. Okay, but what's significant is the numbers. Here is a 0, and there is 180. So this says that is halfway around the Earth. And who found this map? Another few hundred years later, but a man called Christopher Columbus. And Christopher Columbus sailed the ocean blue in 1492, right? And he went, there we go, okay? He went from here to here. Why did he go that way? He couldn't help himself. He couldn't help himself. The Earth spins that way. And all the fluids, that's the atmosphere and the seas, tend to lag back a bit. So what you get is currents. We have currents here. This one, it goes here, starts at the equator and comes up here and hits us. It's called the Gulf Stream. It's named the Gulf Stream by, of all people, Benjamin Franklin. Yes, he named it the Gulf Stream. And it comes from the Gulf up here, past them, and it keeps its heat, and it comes across here and hits Great Britain, which is why Britain has the best climate in the entire world. We just have the worst weather. Okay? I proved that with globe. You go across here, and we're now at Moscow. It gets very cold. And north of that, it's freezing cold right across here through Siberia. It's on the same latitude. Go across here, Canada. You're going across Hudson's Bay. It's frozen for several months of the year. It's absolutely frozen. You can ski all year here. It's freezing, but not here because of the Gulf Stream. That's why we have the best climate in the world. We just have the worst weather. Isn't it lovely? So you see, now that's the thing I have to say. Every classroom should always have an atlas or a globe at hand. Always. You can see so much. You can understand so much about the world using this. And we can understand Columbus went here and he called this place here, which is some islands, he called it the West Indies. The Indies going west. Because he thought, I can stay around here and find the Indies. If you punch a hole through the earth here that comes out on the other side, you come out at the Philippines, which means that Christopher Columbus was half a world away from where he thought he was. Not just wrong, wrong by half a world. However, along came a man called Amerigo Vespucci, and he had the maths, and he understood. And when Vespucci got to the West Indies, he had an almanac that told him when the Mars and the moon were in line on a certain day at a certain time. So he found that alignment and decided he was 82 degrees around the Earth, nearly a quarter. And that's correct. So he knew the true size of the Earth. And he said there must be a whole wodge of land. He couldn't get past the Americas here. He didn't know it's so small, this estuary here near the Panama Canal, this isthmus. He didn't know it was so cool. And he said there must be something on the other side, and it's probably an ocean. Is it an ocean? It is the Pacific. And from about there, you can't see any land. Just a bit of the edge of Australia and perhaps North America and a few islands. So the Pacific covers half the entire globe. And that's why it turns out that Columbus was wrong, Ptolemy was wrong, Poseidon was wrong, but Eratosthenes was absolutely right. And I've lost Eratosthenes, there he is now. Now I'm going to talk about how we do with time. What time do I finish? Tell me what time. Tell me what time the hour will be, because then we can stop for questions. What time will the hour be? Anybody know? I've got 1:05 now. If I'm
Johnny,
heading,
your hour is at 1:45.
That's fine. That's fine. Plenty of time. Right. Okay. I'm going to talk about Archimedes. Archimedes, the wonderful Archimedes. He was quite incredible. Yeah. He was quite. I'm going to show you some of his maths. I'm going to shuffle these. One second. I'll come to that in a minute. What we're going to do first is this. He was an incredible thinker. What he had to do was solve problems when nobody had solved them before, and we didn't have the maths to solve them. So this is one of the problems he solved: the volume of a sphere. I'm not bothering with the mathematical terms, or hardly at all, okay? He wanted to find the volume of the sphere. So he made a cylinder which was the same height and the same width. And he produced two double nap cones. They're called double nap because they meet in the middle, because one's upside down. I had to explain that if you use one cone that height and the same base, then that would be a third of the volume of this. He knew that. A pyramid, if you built the walls from the base of the pyramid to make it a cuboid, right, then the volume of the pyramid will be 1/3 the cuboid it sits in. I've got 3 little cubes that I can fiddle around with. And what I've got is 3 pyramids here, but they're unusual pyramids in that the peak isn't over the center of the base, it's over one corner. And if you get 3 of those, you can, on a good day, the following wind, put the three together to make a cube. Okay, that's the end of that. Right. So this is 1/3 of this. Now, this is the next thing he did. He said, oh, look, if I took a line across here, then the cross section of that equals the cross section of that, because I've made it that way, plus 0 at the North Pole. If, on the other hand, I come halfway down, the cross section of that equals the cross section of that, because I've made it so, plus 0. Wow. So he thought, if I look for a ruler, there will be one hand. Got a set square, that'll do. If I take a line across them at any point, well, the cross section of that equals the cross section of that plus the cross section of that every time. Will it? And he said, I bet it does. So how could he prove it without the maths? He dunked that in water, measured the level of the water, took it out. Dunked those two in the same water, they came up to the same level. Therefore, the volume of that plus that equals the volume of that. Right? That is 4/3 pi r cubed. That is 2/3 of that. Sorry, the sphere. Please, I told you I wouldn't do the actual figures because I confuse everybody. If it's not written down, I confuse everybody as I don't have a living. That is 1/3 of that. That is 2/3 of that. This is pi r squared times 2r. Right? So this is 4/3 pi r cubed. That's what it is. Okay. And he found it. But you see, he found it without any maths, just using his brain power plus the mathematical knowledge he had. And that's the secret. What your students should be learning is how to switch their brain on to going the next level, to going to the next stage. Inspiring in them the desire to go to the next page and look up the next extension of what you learn. That's the secret of maths. And I think it's the secret of all education. And it's fascinating. Archimedes was incredible. They say he produced a claw that could lift a ship out of the water, tip the sailors out, and then dash it against the rocks. Who wrote that? Well, a Roman wrote that. And you have to remember that he lived in a place called Syracuse, which you must go to, it's lovely. And the Romans were very worried because a chap called Hannibal with his elephants had come through Europe, down through Italy, and had conquered several Roman armies, several battles over a couple of years. So they realized that if other people start siding with Hannibal and the Carthaginians, we're going to be in trouble. So they decided to take Syracuse, which is only a city-state, a port, okay? They conquered a city 20 miles north one day. They came to Syracuse with Archimedes, and 2 years later, they still hadn't taken Syracuse for 2 years. So perhaps these stories were made up as excuses. Perhaps they were. Could you really produce a claw that would lift a ship out of without hydraulic and things like that? Could you really do it? You possibly. People have tried to make models of this, and they have. They say that he did all kinds of things. He burnt ships with mirrors. Well, it is conceivable to do it, and it had been done 200 years before Archimedes, or tried. Okay, so that was possible. But what he did was quite incredible. It really was incredible how he kept it at bay for 2 years. But he did something else. He messed around with levers, right? And he said, give me a lever long enough and I can move the earth. Wow. So the question is, how long would the lever need to be? Well, I've got a smaller globe. Just a second. I'll look at my props. Okay, I've got a smaller globe. Right, it'll do. This box is a lever. Okay. If I sit the Earth, and it's a perfect sphere, on the very end of the lever, okay, then the fulcrum needs to be as close to the Earth as possible. Because if you've got a lever and the fulcrum's in the middle, then you need just as much weight down here to lift that up there. So the nearer the fulcrum is to this end, the more leverage you've got. It's the principle of wheelbarrow. If you've got a wheelbarrow, get the load well near the front wheel and get your hands right at the far end, and you can lead. So the question is, how close could you have the fulcrum? Well, let's say the fulcrum was, and the Earth is a perfect sphere. Let's say the fulcrum was 1 millimeter to the right, 1 millimeter. That would give him maximum leverage. So how long would the lever need to be? Well, I worked it out. Other people might, nobody's disputed it. Nobody's disputed it. I've asked people to dispute it if they like, but I worked it out. To do that, how long will the lever need to be? The lever we need to be 1,582 light years. Right? And now he's got to get to the end of the lever. Then he's got to find somewhere firm to stand and hope when he puts his weight on it, it doesn't bend. So it's a bit fanciful, but the principle is right. With a lever long enough, he could conceivably move the Earth just with his own body weight. All right. But that is Archimedes. He was quite incredible. I saw a slide just now, but I can find it. Yes, I've got it. Got it. He explored parabolas. Okay, I'm going to show you this parabola because parabolas are not things you should be scared of, right? If I fold this very quickly. Right, there you go. So what I've got, this parabolic curve is formed with the formula y equals x squared. So here's x going along here, there's 10 of them, but up there, there's 100 of those, all right? So what we got is a series of dots, okay? I want you to give me two, I'll tell you, just give me two numbers between 1 and 12, and I'll multiply them. 5 and 12 would be lovely. 5 and 12, good, good. It works for any number, but I'm showing you clearly. 5, 12. 1, 2, 3, 4, 5. If you take that point there and connect it to the 12 there, it will pass through 5 12s is 60. It will pass through the 1, 2, 3, 4, 5, 6 perfectly. It's a calculator, an automatic calculator, and it's quite beautiful. So explore that. The formula teaches y equals x squared, and that should work. Okay. I'm going to only touch on this. And I'm having to use this box as a ruler because I can't find my ruler. Right? Okay. Basically, using a lever, you can calculate something. So if this is a perfect lever and it's balanced, right? I could put 3 dominoes on each end and they balance, or 1 domino on each end and they balance. But if I put 1 domino in this end and 3 dominoes here, only a third of the way along, then they balance. Okay. And he knew that, and he knew about parabolas. So he was trying to find a parabola. So I'm only going to show you this very quickly. He decided he wanted to find the area under a parabolic curve. Now, this is probably very advanced for the students of the teachers who are involved today. So I'm going to cover it very quickly to show you how incredibly brilliant he was. He wanted, the first drawing we found of it, we've got more evidence of Archimedes' life and his maths than any other mathematician in ancient history, but it's still not a lot. It still isn't a lot, right? But we found this, and we think this slanted triangle was to indicate that it doesn't matter how you manipulate the triangle, the principle of what equals what is the same. So we straighten that out to there, right? And he wanted to know the area of the parabolic curve compared to the rectangle it fits in or the triangle it fits in it, okay? So what he did, he thought, instead of having that rectangle, if I double the length here, double the height there, then that triangle is the same as the rectangle in area. If I double the height, then that's 4 times. So that's what he did. Why he got there, I don't know, but he did. But then he did the most amazing thing. He said, I extend this line here to double the length. I'm going to use a scale. I'm going to use it as scales. So I'm going to drop any line down here, any line down here. And part of it goes through the whole triangle, and part of it goes through the parabolic curve, okay? If I take all these bits and put them here, and if I did it so many times that the lines became solid, you couldn't see daylight through them, then I'd have all of that up here. Now, could I get it to balance this triangle? Well, I could, but the center of gravity of a triangle, did you know this? Center of gravity of a triangle. What triangle is? Must be here. How could it not be here? It's always here. The center of gravity of a triangle. This is quite an amazing thing. If you take the center point of a line of any triangle, it doesn't have to be a right angle, center point, join that to the opposite angle, the center of gravity of the whole triangle is always 1/3 along. Isn't that beautiful? If you did that 3 times, so one to here and one to there, then all 3 lines would go through the center of gravity. It's beautiful, okay? Once again, Euclid, okay? So he said, could that balance that? And he said, I think it does at that point there. And therefore, he knew the ratio between the parabolic curve and the big triangle, then the triangle half the size, which is the same as the rectangle. And he found that the parabolic curve is 2/3 the rectangle it fits in. So he'd done the maths without doing any maths, just logic, just using his brain. Now we do that today playing Sudoku and games like this. That's what your brain is for. Your brain is there to work things out without often being told. And if you can do that and add to what you learn from other people, you will expand your mind and your knowledge and your ability so tremendously. Okay. I'm going to do some Vedic maths here. So what I want to do, this is a bit of practice. I usually practice. So I've got some paper here. And I've got double 9 dominoes, which are as old as me. All right, my dad had double 9 dominoes before I was born 83 years ago. And these are the same dominoes. And there's a double 9 domino, 2 blank. I don't want a blank. The last thing I want is a blank. So how can I multiply 2 numbers if one is a blank? 3 and 9, right? What I'm going to do is multiply numbers just over 100. So I'm going to multiply. This is without rehearsal. This is without me warming up. Oh, I do hope I do this okay. 100, write them down. 103 and 109. And I'll tell you the answer. 27. Oh my God. I'm sorry I can't do it because I'm panicking and my mind won't work. So I'm going to show you how it works. Right? I'm going to take 2 more and see if I can. If I'd warmed up, I'd be able to do it, but I'm actually coming out in a cold sweat because I haven't done this for months and months and months and months and months. I'm going to multiply 2 more numbers, write them down. 90s, number in the 90s, 93 times 95. And the answer is 8815. There, I did that one. Oh no, I've got it wrong. 8835. Okay. It's very good of you to come to my rehearsals, everybody. Do you know what I gave up for Lent? Rehearsals. That's what I gave up for Lent. Okay. I'm going to show you that multiplying 2 numbers in the 90s. And this is Vedic maths, and it's very powerful. So 93 times 95. The bigger one, 95, you take from 100, it's 5 less. So you take 5 off the 93, you've got 88. Okay. That's the front end done, right? You take that from 100 and that from 100 and multiply them, 7 5 35, and that's the answer. Okay, is that right? Yes. Okay, thank you. So what's the over the 100 one? Right, here they are. I've written them down because I'm scared. I do this in my roadshow and I do it absolutely perfectly every time, I assure you. So multiplying 92, 94. 94 is 6 short of 100. So you take 6 from the 92 is 86. That's the front end done, right? Take both from 100 and multiply the 2, right? 8 and 6, 6 eggs are 48. So they are, and 8, 6, 48. That's how you do it. Vedic maths. It's really fascinating, Vedic maths. People say it comes from the Vedic period, which is 2,000 years ago, at the same time as Christ in India. But I think this has actually come from about the 1950s. I think that's when people latched onto it and started to use it. But if you look up Vedic maths on the web, get your students to do it, and what you do, you get lots of things. Go to images of Vedic maths. Go straight to there, and you'll see all the examples, and you'll see how powerful it is. And it's really, really great fun. Okay, right. Numbers are called called Arabic numerals, but it was from the Hindus that the numbers came via Islam. Islam has to be credited with creating the Renaissance in Europe, because if the numbers and other things hadn't come after the Crusades, which were a tragic waste of time, but after the Crusades, so much information came over to Europe and filtered right through Europe up to Great Britain, including Arabic numerals, which we call, and they have empowered us ever since. They caused the Renaissance. So you can't underestimate how wonderful Islamic maths was at the start. And some of these Islamic mathematicians were great inspirations for later mathematicians in Europe. And one was called Ibn Sina, or Avicenna, as he was called in Europe. And he played with numbers, right? In fact, he played with odd numbers. He said, isn't 1 funny? 1 times 1 is 1. But 1 times 1 times 1 is 1. But 1 times 1 times 1, funny number. So then he looked at the next 2 odd numbers, 3 and 5. 3 plus 5 is 8. What's 8? Oh, it's 2 times 2 times 2. So let's take the 3 next odd numbers, 7, 9, 11, 27, 3 times 3 times 3. The next 4 odd numbers, 4 times 4 times 4, 64. The next 5 odd numbers, 125. The next 6 odd numbers, 216. And this process goes on forever, forever. And it shows the beauty of maths. Now, if we're doing numeracy, to do things like this in numeracy, really that enlivens us. And it gives us an artistic feeling. As an artist loves to paint and get a proportion and get something right, suddenly you're doing art with numbers almost. And it's so much more exciting. So what you've got to do in schools is teach the maths you're asked to teach in 2/3 of the maths time, please. Cram it in. It's a bit difficult when half your class are away on COVID leave. It's very, very difficult. So at the moment, it's impossible in education for us to be functioning very well. And I feel for all teachers and everybody in education at the moment, it's frighteningly difficult. But the kids will still come through and they'll still learn and they'll still take the same positions that they would have. It's almost, you almost survive irrespective of your education. You really do. And you've got to convince the kids that this is the case. And anything you get wrong in education is repairable when the student is in the right mindset, which might not be till they're 22, 24, 30. Could be then. But everything is repairable. So please don't let your kids worry if they're suffering at one level in school. It's only temporary and it can be resolved. Okay. This is Ibn Sina. Okay. Here's a chap you'll know. The chap who produced this. This is Leonardo da Vinci. And I do like to show this. You've probably all seen it. It's called Vitruvian Man. And what it is an aid to measurement. So it's lovely to explore. In fact, one thing you can do with kids, I've always done with primary kids, you get kids to Get to a wall and put one finger down on the floor and stretch as high as they can with the other middle finger and mark that point on the wall with pencils. You can rub it out. Okay, then when you stand, you'll probably find the height of the person is very, very close to that reach of the two arms out. And that's what he found here. So the man is in a square, and that is a stature. Your stature, your height, stature comes from that, and that is your stature. It used to be a fathom, and seafarers use fathoms. Half a fathom is a yard, half a yard is a cubit. Now my cubit, if I can show you this, my cubit is exactly 18 inches, which is what it used to be, 6 foot, 3 foot, 18 inches. And half of that's a span. And sure enough, 2 of my spans reaches the 18 inches. It works, okay? So there's an 80 measurement. What point of your body is halfway up the human body? It is your navel. No, it's not. Halfway up the human body is your hip bone or your pubic bone, which I've hidden with a fig leaf, but it's there. That's halfway up the human body. Okay. This is 8 spans across, 8 spans tall. The navel is 5 spans from the floor. It's a span higher, right? And that is the center of the circle. Okay. And it's a lovely mathematical thing. But the reason I show you this is because the secret of all education is here. The secret of all education. Where did Leonardo get the idea from this picture? He nicked it. All education is theft. You are stealing from the people who've gone before. So if you're going to steal, steal from the best. That's why we talk about the greatest scientists. Steal from the best. That's what we've all done. All our technology is based on ideas from the best. And the people after them have got better and better and better. It's how it works. The whole human race is in a relay race. And the generation you're teaching now will pick up the baton and will take it further than any generation before. And every one of your students can be part of that because there's so many branches of human activity. So there's so many places you can achieve and actually take the baton further and do something that nobody has ever done before. That's the possibility. That's the potential of every one of us. And that's great. He called this Vitruvian man because he nicked it from Vitruvius, who lived, I think, 1200 years earlier. He was a great engineer, Roman engineer. It was Vitruvius who told us about Archimedes jumping out the bath and running down the street in the nude, shouting, Eureka. Everybody else is going, Eureka. Right. So that's Vitruvius. And Vitruvius approves this. But it's an improvement on Vitruvius. And it's much, much better, right? I'm going to show you something now. A lady called Germaine Greer, a great feminist, right? And always very controversial. She was talking at Hay Literary Festival. And she said, why do we go mad with Leonardo da Vinci's painting? I don't think he was that good a painter. And I agree with her. Why? He didn't want to be. The only painting he did after this was the famous painting. Hey, God, not the fallen Madonna with the big boobies. No, help me, Leonardo's Mona Lisa. Okay. I'm at an age, you see, where my mind would go blank on the most amazing thing. Right. It was the only picture he painted. Why? Because he discovered mathematics, right? And he wrote, anyone who performs art who doesn't understand mathematics is wallowing in a dark cavern, something like that. You're wallowing in the dark if you don't understand the maths. So once he started on maths, in fact, he worked for a chap called Leo Morrow for 16 years. And when he left, the lady wrote to him and said, I'm sure you have time now to paint my portrait. And he had somebody else write back and said, Da Vinci, Leonardo, cannot paint your portrait now because he's discovered mathematics and he now cannot stand the sight of a paintbrush. True, absolutely true, right? And he discovered maths. To what extent? Well, I'm going to show you this. Now, it's very difficult to see this. But what you got is two pieces of paper, right? Or one piece of paper that's been folded. Okay, it's one sheet. And there are rows, and each row is about that depth. And they're all they're all semicircles, or most of them. They become circles later on. And they're all divided with other curves and things. Do you remember I told you how you measure a square root using a semicircle? Well, you can do all kinds of other maths using semicircles. So he explored it all. He became a total anorak with geometry, just on circles, a total anorak. So your students today, I hear they're going to ban phones in school. Hooray! Good heavens! Thank goodness for all you teachers. If you've got an official word that is banned, that's what you need, not your whim. The actual official. Phones are banned. That's the way it's got to be, right? Because otherwise, you cannot hold your students. But students have got to realize this. Now, your students may be wasting a lot of time on computer games. Is that terrible? Not necessarily. Why? Everything we do is habit forming. Everything we do that we like, we do more of, and it's habit forming. So anything becomes habit forming. So if concentrating on something, as in a computer game, is part of your build up, then later on, applying that same concentration to something that matters, like a degree course, can be the difference. So it's all part of training. It's natural for us to be repetitive as we learn. It's natural as animals. So you've got to then say, well, you can feed that in later. And once your students get the bit between their teeth to go with something, they can and will put the hours in and succeed. And that shows all this. Right. Okay, that's fine. I've got another 10 minutes or so. So I'm going to go ask a question here. We're going to do a bit of maths and science. Okay. Who was the greatest British scientist of all time? Carol Vorderman. No, hang on. No. Isaac Newton, because they discovered the force of gravity. Rubbish. This I'm going to straighten out for you to show you that education and discovery and science is all a conveyor belt. It's all a moving staircase. It's all one person. It's all a relay race, picking up the baton and carrying it further. That's what it's all about. COVID is a wonderful example. The way the medical fraternity got together and often leaning on each other have produced the drugs that they produce so quickly is a total accommodation for science and the ability we have. Now, if we can solve that problem or those problems within the scope of a year, there is not a problem on earth we cannot solve. Plastics and weight and things like that. We can solve them all. So I cannot stand people who instill in kids a fear that the whole world's coming apart. I cannot stand it. We have the ability to improve everything. We've just got to follow the right track and make the right decisions to improve it. Okay, not the wrong ones. And not start marching, oh, we've got to stop all this and wasting everybody's time. Okay, that's my feeling. So who's the greatest British scientist of all time? Isaac Newton, because he discovered gravity. Rubbish. I'm going to explain how gravity is made. There's a lad called Galileo. I've got it. He was a poor boy from a poor family. Galileo used to go to Pisa Cathedral, and when he was 17, he noticed something. The chandelier swung, and it was swinging, and he sort of timed it. And then the following week, there was a bit more swing. And then the following week, so he went tick, 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 tick. Following week, more swing. Tick, 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 tick. Following week, hardly any swing at all. Tick, 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 tick. And he said, it's the same tick. He was a soppy lad for 17. It's the same tick, 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 the same tick. So he thought, what can I do? Because he went home and he made one of these. I thought, what can I do to make it swing faster? What could I do to the string to make it swing faster? I could shorten the string. How much would I shorten the string to go twice as fast? Half? Let's try it. Tick, 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 tick. That doesn't work. Twice as fast is not that. So we'll try a quarter. Okay. Tick, 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 tick. Oh, nearly. Tick, 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 tick. Twice as fast. A quarter of the string. 1/4 and 3, and then 3/4. Right. He was coming past the Leaning Tower of Pisa one day when a slate came off the roof and fell and missed his shoulder by that much. It hit him on the head. So he thought, I can do that. I can drop bricks off buildings. Actually, all those experiments were done by a man called Stevin, a Dutchman called Stevin, and he did them before Galileo, and he should get the credit. But we give it to Galileo. That's the way science is sometimes. It gets weird. But Galileo did lots of things, and I'm going to cover them very quickly and show you what he discovered. He found a ball dropped not off the Leaning Tower of Pisa. He never said he did that. Other people said he did that, and he'd never mentioned it. Okay, even though it was there. The cathedral's taller. He could have done it off the cathedral, right? However, he couldn't time it because it was speeding up, and he just couldn't time it. There were no watches in those days, just a handful of clocks, and the clocks only had hour hands, didn't even have minute hands, right? So what he did, he slowed it down and he rolled. Now I can do this, but I'm not doing this today. So he rolled a ball down a slope, and it doesn't matter what the slope is. He found the mass is always consistent. However far, he used ticks again, right? Tick, tick, tick. So he let the ball go, tick, 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 and he measured where the ball was for each tick. He took 3 months to do this experiment before he was happy with the results. 3 months. He used every slope, every angle, and he found it was all the same. However far it went in the first period of time, in the second equal period of time, it went 3 of them, then 5, then 7, then 9. All the odd numbers in order. The maths couldn't be more beautiful, simple, and clear. Adding as we go along, it's 1 unit. Plus 3 is 4 units. Plus 5 is 9. Plus 7 is 16. Plus 9 is 25. They're all square numbers. Everything that rolls downhill or falls increases speed by the square of the... Look, I haven't done this for a while, right? It's always the square of the time taken, okay? So in 5 units of time, it's gone 25 units of distance, okay? Then, you could try this with your students. You could tell them, go off the cliff on a bike. No. Go off a cliff on somebody else's bike. That's essential, right? But if you go off a cliff, the distance, you could go off with a car and you get a wider sweep. Of a bike, it would be close. If you just walked off the cliff, you go straight down. Don't try it. But imagine it, right? Okay. So the distance going this way doesn't change, but the distance down does. If in the first unit of time, it's gone there, 1 unit. In the second unit of time, it's gone 4 of them, then 9 of them, then 16, then 25. And this is a parabolic curve. To celebrate discovering this, he went out to fire a cannon and explained exactly the same mass. Fire a cannonball, and it wants to go in a straight line forever, but it doesn't. It falls to earth, pulled by gravity, which nobody had discovered yet. But he knew the maths. If in this distance it falls 1 unit, in this distance, twice as far, will fall 4 units, then 9 units, and form this parabolic curve. And he discovered all that. And then he died. He was old when he died. He had a friend called Johannes Kepler. When Johannes Kepler was a German, and being German, he spoke like this. Here's what I'm finding. I've been accused of being racist. I will not stop doing jokes like that because people think there's just something wrong with it in these days. I think a German accent is lovely and beautifully funny, and I wouldn't harm a German or a German person at all. So I'm still sticking to that. Okay. So Johannes Kepler. He said, here is what I am finding mit my Ball und String. I am finding as the planets circle the sun, they do not circle the sun in circles. 999. Because if I stop spinning the ball stoppen spinnen. But if I'm giving a slight pulling, the ball keeps spinning, not in circles. They are ellipses, shorter, longer, shorter, longer, shorter, longer. He found the planets were going around the sun in ellipses. He said, I find planets far the sun go slowly, near the sun go faster, out slowly, in faster. How did I get this job? I pulled strings. Then he asked the question, why is it happening? There is no string on a planet. So there must be a force acting like the string. And the force must be stronger here and less strong there. And he worked all the maths out and he died. And along came Isaac Newton. And Isaac Newton made one of these because Kepler had made one. And Robert Hooke made one. And there's one in the Royal Society Library made by Robert Hooke. And when I asked if I could show children in the Royal Society how it worked, they said, oh, no, you can't touch it. Well, if you can't touch this thing, what is the point of it being there? See, and this is beautiful. So please make one. You can use a roll of tape, anything. You do need a tube so you can lengthen the string and make one. And you will find, as Newton said a planet here requires a certain force to hold in orbit. Planet twice as far away, only a quarter of the force is needed. Planet here, certain force. Planet half as near, 4 times the force is needed to stop it spinning off into space. And that is the same maths. And so what did Isaac Newton do? He read 2 books. He read Galileo's book, Things Falling on Earth. He read Kepler's book on the planets. And he came up with gravity. We are told it was thinking about apples falling from a tree. A very, very famous mathematician said, if he said that, he was clearly talking to an idiot because it's so simplistic and it couldn't be that simple. He said it in the last year of his life. But what he actually did draw was this. Okay? And he drew this and it was found after he died. And he says quite clearly, if you throw a ball sideways, it will fall to earth. Standing on the top of a hill, throw it harder and it will still fall to earth. But what if you could throw it superhumanly hard? Then it might fly the earth in parallelation, all the borders of this nation, across the ocean's aquilation, round the earth's great globulation, and like the moon in its gyration, describe a perfect circulation, arriving with unexpectation at my rear side elevation. Ooh, eureka, what a revelation. Methinks I've discovered gravitation, for stone and moon in their gyration desire a true delineation. They want to go straight on without deviation. So why do they go around in circulation? It must be the Earth's weight and gravitation. The Earth's great weight is the persuasion that holds us down to our frustration, and the moon's acceleration equals the pull of gravitation, causing it without cessation to turn in constant revolution. Furthermore, every particle in creation is attracted to every other station. And that attraction is in relation to their dual mass combination and also in inverse relation to the squares of their separation. These laws of universal gravitation, the results of his amalgamation, were due cause for celebration, not with somber meditation, but with elation, affectation, and highly mirthful levitation. He was only known to have laughed once in his entire life, so it doesn't really fit him. But there you are. How have I done? That's about time. I've gone through the history of maths to show that if we get really into it and really understand it, it is fascinating. And you see that not one genius did anything that wasn't possible according to the time he lived and the information he had. Not one genius did anything totally out of order, totally on a new field. It was always a development of others. And that's what you have to tell the students. And your students can be part of a brighter future, because the future, please don't teach doom and gloom to your students. Please do not. Please point out, as is the case, I've been around for 8 decades, all right? And I've seen, I did a drawing, and I've seen how every 10 years, everything has improved, and far more things that have gone worse, everything improved. And it will happen with them. So the worries and the doubts and the marching and the complaining, there's no room for it. There is room only for being positive, that your students have the ability to improve the world and be part of that improvement. There you are. Thanks for listening.
Thank you so much, Johnny. That was so fascinating. I loved every single minute of it. I do think there's an opportunity for some questions coming in if people would like to add in some questions, which is absolutely fine. I have one for you. We don't have loads of time, but I thought I'd love to know, where did your curiosity for geometry come from?
Yeah, right. I was brilliant at maths. My dad loved maths. The double 9 dominoes, I could play before I could hold them up. So my numeracy was fine. So I was always top in maths. I went to school in Bolton, and I just lost touch. The teacher lost touch with me. I had a Bristol accent, and before television, a Bristol accent in Bolton was like speaking Urdu. It was like a foreign language. So I was allowed to gravitate to the bottom, and I got 2 O levels. And then I got 100% in maths. It's always been there. My love of maths has always been there. So I started, because I didn't do university, I was in the RAF in 3 years, and that was my university. And I learned so much. And I learned, go out, reach for it, and you can achieve it. And that's what the RAF told me. So I've had this upward trend after terrible schooling. This upward trend, it just continued. And so my confidence built and built. And I've had a wonderful career, absolutely wonderful career, starting as a failure. So do remind all your students of that. My enthusiasm for math is just there. It just is. And especially geometry. It explains so much. Just a few lines, as Galileo said, just a few lines and a few angles, and you can absolutely calculate anything. It's marvelous.
Yeah, absolutely. I think I definitely had a love of geometry as well when I was growing up. I think it's definitely one of the ones that I think it sparked my, I suppose it sparks your creativity. You look at things in different ways to other people. You start thinking about things differently. So I used to really enjoy it. I think as well, because I thought a little bit differently to everybody else. I didn't always follow the set way of doing something. So it's so nice to...
you can acquire a mathematical eye.
Yeah.
You can acquire an eye where everything you look at, if you look at it from a mathematical point of view, suddenly it's clearer to you, even before you've been told anything about it. And that's the joy of it. And it does empower you. And it's wonderful because you feel that empowerment very often when you meet something new. Oh, that links to that, and I got it. Yeah, fine. And it's wonderful. Maths is by far the most important thing you do, and the geometric side is the most important of all that.
Yeah, absolutely. Well, I think we are a bit out of time right now, so I think I'm going to say thank you so much, Johnny, for your time and going through that little short history. Do you want to say anything else? Yeah, please, everybody, as there's not time now, email me. So that's jballpros@aol.com, or just Google Johnny Ball and you'll get johnnyball.co.uk. Come onto the website, you get the email there, and my phone number. It's all there. And I love people to contact me for any reason at all. And I usually get a reply. Okay. I'd just like to echo that as well. Anyone who wants to contact White Rose Maths, we're more than happy to answer any of your questions well. We're obviously on the same agenda as Johnny. We want everyone to love maths. We want everyone to have a curiosity about maths. And we believe everyone can as well. So thank you for listening, and I hope you have a great rest of the festival. Bye for now.
Thank you. Thanks, everybody. Bye.
Bye, Johnny.
It's my great honour to welcome you all.
It is a very prestigious award. It means the world to me.
They have great senses of humour.
I like to reveal parts of history to them, for I love making history come alive.
They are some of the best people that you can come across.
To help them open their hearts.
I always come back to this quote. How can we be role models to learners if we're not learners ourselves?
It's quite useful to get out of our bubbles, not our COVID ones, and sort of see what else is out there.
By sharing best practice, we can see the whole picture. We can see what really matters.
One of the biggest brains around.
It's easy to forget how much has to happen behind the front lines.
As a global schools group, Cognita educates over 55,000 students across 12 countries. We're proud to be Wellbeing Partner at this year's Festival of Education, and we want to share the work that we're doing to prioritise children's well-being. This starts with a clear understanding of what well-being is. We looked at the evidence and created a simple Be Well charter that everyone can use day to day. It gives a clear definition of well-being and then focuses on the specific contributors that influence it. Discover our full Be Well charter video and other resources to use with your students and families at cognita.com.
I really try to not look at myself as just a science teacher. I feel like as a teacher, it's very important to help students grow and develop outside of your lessons. A single teacher believing in you and really believing in you. One teacher doing that can have a large impact, but if you have one or two or three all telling you that and really, really believing in it, it makes you feel like you can achieve anything in the world, honestly.